Okay, so thank you very much, and good afternoon to everyone. My name is María José Fabra. I'm coming from the Institute of Agrochemistry and Food Technology, which is located in Valencia, Spain. And the topic of this presentation is innovation in food packaging, which corresponds to the session 4 of the common training courses. I have selected some slides from the different units, bio-based and biodegradable materials, active and smart packaging. And if you want to know something more in detail, you can visit our website, each unit of session 4. So a wide variety of materials has been traditional use for food packaging applications. However, nowadays plastic and polymeric materials represent the main packaging materials used for food packaging. In particular, plastics and polymeric materials present several advantages as compared to other traditional packaging materials, such as versatility of processing methods and interesting cost-performance ratio. Furthermore, these polymeric materials are light, they present other advantages such as light, weight, reduced cost, and they have good optical properties that can be adapted depending on the food requirements. These polymeric materials can be printed, thus being able to provide information to the consumers. In addition, these polymeric materials can be processed as a part of integrated processes in the production line, which are formed, filled, and sealed in the same line. However, one of the main disadvantages of using these polymeric materials is that they are not biodegradable. They are mainly petro-based materials, and they present a slow degradation rate. Furthermore, recycling and reusing are not fully suitable methods for all packaging materials used in the area of food, because in most cases they are multi-layers. Thus, there is a worldwide general problem derived from waste management because of the high plastics consumption. Therefore, from the food packaging application point of view, great efforts should be focused in order to extend the shelf life and to improve food quality while reducing plastic waste. Consequently, there is an increasing great efforts are being developed in both academia and industry for the development and implementation of bioplastics. Bioplastics, also known as biopolymers. In this figure, you can see the global production capacities of bioplastics in the recent years. And it is clearly observed there is a sharp increase in the last years, mainly in the food packaging area. One thing that we have to be in mind is that biodegradable is not the same as bio-based. Biopolymers are bio-based, biodegradable, or both, and bio-based that not equal to biodegradable. In this figure, we can distinguish between fossil-based, bio-based, biodegradable, and non-biodegradable material. As you can see here, we can find materials we come from biomass, and they are biodegradable, such as starch, PLA, PHA, which are the more common, but there are others. There are another group which are fossil-based materials, but they are biodegradable. Among them, we can find PCL, which is the polycaprolactone, which is widely used. There are other materials that come from biomass, but they cannot be degraded, such as many cellulose derivatives. And the other one is petro-based materials. We come from fossil-based, and they are not biodegradable. So renewable refers to the reaching of the carbon atoms in the polymers, and biodegradation by microorganisms is a matter of polymer structure, not the carbon origin. Biodegradation is the chemical process during which microorganisms that are available in the environment convert materials into natural substance such as carbon dioxide, water, and compost. And they don't need artificial additives. Biodegradation depends on the surrounding environmental conditions, location and temperature, also on the material and their application. And as I have already said, biodegradable is not equal to biopolymer. Here are some definitions from the STM and ISO for degradable, biodegradable, and compostable materials. Degradable undergoes a significant change in the chemical structure under specific environmental conditions, resulting in a loss of some properties that may vary as measured by standard test methods appropriate to the plastic and the application in a period of time that determines its classification. Biodegradable plastics are degradable plastic in which the degradation results from the action of natural occurring microorganisms such as bacteria, fungus, and algae. And compostable materials or compostable plastic materials undergoes degradation by biological processes during composting to carbon dioxide, water, inorganic compounds, and biomass at a rate consistent with other non-compostable materials and leaves not visually distinguishable or toxic residue. Materials can be photodegradable by the action of sunlight with the daylight. They can be also oxidative degradable material by the action of oxygen, or they can be degraded by hydrolytic action. In the case of biopolymers, we can find different types, 3 different groups of biopolymers. Those directly extracted from biomass, which are mainly proteins such as gluten and zein, but also polysaccharides such as starch or cellulose. There is another group which they are classically synthesized from biomonomers such as polylactic acid, and the other groups refers to materials directly produced by microorganisms such as bacterial cellulose and polyhydroxyalkanoate. Among the most widely studied thermoplastic materials, starch, PLA, and PHA have attracted particular attention because they are commercially available. They can be processed by the conventional equipment that we use for petro-based materials. They can be scaled up, of course, and they have relatively good properties for many applications. In the case of starch-based biopolymers dominates the market of biopolymers. It's economically competitive to petrochemical materials, and we can obtain starch from maize, tomatoes, wheat, and rices. Depending on the raw material, we have different starches which vary in the ratio amylose-amylopectin, and thus the resulting thermoplastic material will be different. The general properties of starch-based materials is it is hydrophilic, it's brittle, the mechanical properties are lower than petrochemical-based polymers, and in general they present low resistance to solvent and oils. However, their properties can be improved by the addition of plasticizers such as glycerol or sorbitol, and also by blending this starch with other biodegradable materials such as PCl. Here we have, I will show you some commercially available materials, biodegradable material based on starch. For instance, Matter V, which is based on starch and a mixture of starch and PCl, which is a biodegradable material which comes from fossil-based materials and is the European most common bioplastics. But there are other starch-based materials which are commercially available. However, as I have already said, starch-based materials have some limitations because these materials are high hydrophilic. Polylactic acid is another interesting biodegradable material which can be obtained from corn. after a fermentation of a starch, we can obtain acid lactic, which can be, and from this acid lactic acid, we can obtain oligomers, and by polycondensation, we obtain the PLA. PLA is an aliphatic polyester with polar character, which physicochemical properties are similar to the PET, which is one of the most common petro-based material. And this material, this PLA, has limited barrier properties compared to the benchmark PET. However, it can be processed by the conventional equipment used for petro-based materials, the traditional packaging materials such as injection and extraction. And this material is biodegradable, it is compostable, and it degrades in between 60 and 180 days. Here, some barrier properties, oxygen, carbon dioxide, and water barrier properties of PLA as compared to other synthetic materials. As you can clearly observe, barrier properties are lower than the synthetic materials. However, this can be used as a positive point to develop active biopolymers for food packaging, as I will explain you later. The main producer of PLA, this is commercially available, is Nature Works, but there are others that also produce PLA. And we can obtain PLA from glucose, from maize, but also from lactose from whey. We need acid lactic to produce PLA. There are other PLA, materials-based PLA that can be used alone or in a mixture of different biodegradable materials. And the main drawback of these materials is that it is sensitive to temperature. Another interesting biodegradable material is the polyhydroxyalkanoates. These are polymers that bacteria produce under conditions of low concentration of important nutrients, typically nitrogen, but sometimes oxygen, and high concentration of carbon dioxide. They produce some granules intracellular, which are the PHA. Bacteria store PHA granules for later use, and we can obtain these granules, we can extract these granules to produce bioplastics. The yield of PHA obtained from the intracellular inclusion can be as high as 80% of the organism's dry weight, and we can obtain different types of PHA depending on the organic substrate. Different properties. We can obtain PHBV, PHBV, which is a copolymer of the polyhydroxybutyrate. This biopolymer is highly dependent on the relative humidity, which is one of the main drawbacks of biopolymers, and they can be processed by the conventional equipment such as injection or extraction. Furthermore, it is biodegradable, and it is compostable, and it degrades between 60 and 180 days. One of the most common PHA materials is the polyhydroxybutyrate, PHA, which has similar properties to the polypropylene. It's more hydrophobic than starch and PLA. They have high aroma barrier properties, but it is fragile. They have high crystallinity. PHB can be degraded. The degradation rate depends on the microbial activity, humidity, and temperature in pH, and it can be degraded in aerobic and also in anaerobic conditions. It is compostable in a wide range of temperature. At 85% of relative humidity, the PHA degrades in 50 days, and in marine condition, it degrades in 9 months at temperature lower than 6 degrees. There are also PHA that are being commercialized by different companies, and we can obtain different types of PHAs, as I have already said, with different thermal properties and mechanical properties that we can use for different food applications in the area of food. But it is only processed by injection molding. Okay, yes, I have already said these polymers, these biopolymers, have lower barrier properties than their counterparts petro-based materials. However, this negative aspect we can use as a positive point to develop active packaging materials. Active packaging systems are designed to incorporate components that will release or absorb substance into or from the packaged food or the environmental surrounding the food. This active packaging can be absorbers or emitters, absorbers as active escaping systems, and as emitters, active releasing systems. Why we can use, or which are the application of these active packaging materials? To preserve the quality of food during the shelf life, we can use antimicrobial packaging for food application to extend the shelf life and to improve food quality, to increase food safety, to extend the shelf life of the food product, to increase food loss, to reduce the use of food additives, because if we directly incorporate active compounds, antimicrobial or antioxidant compounds into the food, the amount will be higher than if we use these active compounds in the packaging material. Also, we can use as a marketing tool and to develop new products. Which is the mode of action of these active materials? There are different modes of action. The modification in the headspace composition, producing a selective permeability, the release of carbon dioxide, for instance, substance that retain or releases gases and vapors. But another mode of action can be modification of the headspace composition by releasing active substance to the food, which antioxidant or antimicrobial properties, or also aroma compounds. I will give you some examples later. Substances that absorb food components, which are not desirable for food. And another mode of action is temperature regulation of the packaged product, regulation of temperature, self-cooling and self-heating. So how to incorporate this active substance into the packaging? One option is to use sachets or pads which are placed inside the package. The active compound is visually presented in small bags, like in this photo, or labels of permeable material which are introduced into the container. What's happened that the presence of these strange compounds inside the container can produce a possible rejection by the consumer, and the greater complexity in the packaging technology and possible toxicity due to circumstantial contamination. Another option is to incorporate these active compounds directly into the packaging material and to provoke a controlled release. Some examples, we can use oxygen escapers as a sachets, or also incorporating the ingredient, the active compound, into the polymer to improve barrier properties by acting as an active barrier, but also to remove any residual oxygen present in the food package. Which ingredients are used as oxygen escaper? Methyls, methyl oxide, and also some enzymes such as glucose oxidase. Another application is as carbon dioxide generating systems. Sachets that absorb carbon dioxide are not usual, and the most common is carbon dioxide emitters that have a bacteriostatic property, bacteriostatic effect in foods. High levels of carbon dioxide inhibit surface microbial growth and extend the shelf life. For instance, we can use ferrous carbonate or a mixture of ascorbic acid and sodium bicarbonate in meat or in fresh vegetables. Another application is as ethylene scavers in fruits such as apples, kiwi, mangoes, tomatoes, or carrots. And the ingredient that is used for ethylene scavers is potassium permanganate. We can use also develop these active packaging materials for humidity control to control the water condensation in some vegetables, in fruits and vegetables, and thus to reduce the growth of mold. Which type of ingredients of substances we use to develop active materials to control humidity? These are amphiphilic molecules. Also, we can use antioxidants for the development of active films for fresh meat to enhance the stability of myoglobin in the case of fresh meat. And we can use also cellulose pads with some antioxidant compounds. These active packaging materials can be used to improve sensorial properties of the packaged product, such as flavor or odor absorber or releaser, and also as an antimicrobial packaging. We can use antimicrobial packaging to extend the shelf life and to improve food quality by using essential oils, plant extracts, natural plant extracts, but also we can use enzymes. Types of active pack. We can use systems that retain or eliminate food compounds such as humidity, oxygen, carbon dioxide, or undesirable substance and bad odors. We can use systems that release compounds to the food such as carbon dioxide. We can have bacteriostatic properties. We can use antimicrobial to be with a controlled release to the food, antioxidants, functional compounds to impart bioactive properties to the food, and also aromas. Other active systems are self-heating and self-cooling. Some slides about smart packaging and which is the difference in smart packaging and active packaging. Smart packaging is a packaging system that is able of carrying out intelligent functions like detecting, sensing, recording, tracing, communicating, and applying scientific logic. This smart packaging informs the consumer the state of the food product and the quality of this food product. Which are the applications? The applications is to facilitate decision making, to extend the shelf life, to enhance safety because the consumer can evaluate the status of this food, to provide information, to improve quality, and to warn about possible problems. Some examples, you can go to the website and you will find more examples of smart packaging. In here, some examples for quality indicator. This is commercially available. It's oxygen detector, which is a detector that changes the colors dependent on the oxygen concentration. If the oxygen concentration in the atmosphere is lower than 0.1%, the indicator is pink, but if it is higher than 0.5%, the indicator changes to blue. There is another quality indicator, which is ripeness, ripe sense, which indicates the ripening of fruits, and this sensor changes color when it reacts with aromatic compounds. We can see here that it can change from yellow to red depending on their status. Another quality indicator is Monitor, which is also commercially available, and indicates the moisture changes in the packages, either in the headspace or outside. And depending on the indicator, we have different colors. It can change from blue to pink or to yellow to green, from yellow to green. And thus the consumer has the information of which is the humidity of these materials. Another one, which is based on sensors, is food sentinel systems, which is capable of continuous detection of contamination. It's based on immunological reactions occurring in part of the barcode, so we can easily detect if there are changes in food. The barcode is rendered unreadable by the presence of contaminating bacteria. And here you can see some of the commercially available sensors, indicators, and dispositifs that we use for smart packaging. That's all, and thank you for your attention.